So over the course of the next 45 minutes, I'm going to be talking about some of the workflows that you need to adopt for CFD simulations and some of the softwares available, some fundamental principles out there. We'll deal with turbulence modeling, which is actually an essential part of CFD, and then an important the closure problems. And I would illustrate with an example actually. So these examples involve designing of a mixer for crystallization of active pharmaceutical ingredients, so which is really important for healthcare. Anyway, so CFD is actually a branch of fluid mechanics where we are actually seeking numerical solutions to the governing equations of mass, momentum, and energy. That is generally what CFD is all about. Now, there are a number of applications in chemical engineering where CFD has been quite useful. And this list is not exhaustive, but I'm just going to illustrate with some examples. For instance, if we take a conventional shell and tube heat exchanger, for instance, and you can actually leverage CFD to improve its performance, the overall heat transfer rate, and by so doing, you actually minimize the equipment size and cost as a process in the process. Now, the next example is actually very interesting. It's intriguing. This involves a catalytic microreactor, where here you want to design, you want to find an optimal catalyst distribution within this microreactor, because it's a pressure-driven flow, basically. So if you have too much or high levels of catalysts in there, what happens is you minimize the flow rate, but then you might actually get a high reaction rate. On the other end is that if you have too low of catalysts, your reaction rate is minimal. So the overall, the goal here is for a given pressure-driven difference, you want to find the optimal catalyst distribution in the reactor to be able to maximize your reaction rates. Now, it turns out that employing CFD, the optimal the optimal catalyst distribution is actually something that mimics tree roots, which is that for a given pressure difference, nature actually looks at, well, how should these trees distribute their roots to be able to maximize on that process. So this is quite interesting as well. Now, another example is that if you want to actually design artificial lungs, which is a form of membrane, you can actually leverage CFD in this case to optimize or even come up with quite interesting designs for artificial lungs. There are more conventional chemical engineering applications of CFD, which is cyclones, which acts in the form, which are based on centrifugal forces as well. So other examples are stirred tanks, where you have impellers. You want to look at what are the optimal positions. Do you need baffles in there? How many impellers do you need to be able to actually improve the mixing in stirred tanks? So you can leverage CFD to optimize some of these applications as well. And then very conventional fluidized bed reactors, which are used in catalytic cracking as well. So CFD has many applications, and by no means is this list exhaustive. Now, if we move on, you might probably be looking at, okay, well, what are the core stages, for instance, and what are the popular packages out there for you to actually use? Because when you first start CFD simulations, for instance, you are most likely not going to be writing your own codes from scratch. So there are popular packages out there, and these are just some of the packages that I ended up interacting with. So you have COMSOL Multiphysics and also ANSYS Fluent, which are paid commercial packages. But one thing I must point out here is that for ANSYS Fluent, there are student versions as well. You are limited to the number of mesh elements that you can actually use, but you can give it a try and see how that goes with that. And then OpenFOAM is a free package, but the learning curve is relatively steep, and so you have to you can look at that as well. But one thing I must point out here is for OpenFOAM, you have to work in Linux instead of Windows. So those are some of the challenges out there. Now, with all of these packages, the steps, there are three main steps you would typically have to involve in, which is that you would start with a pre-processing step where you define your geometry, you do your mesh, and the physics, as well as the boundary conditions. And then you move on to the solution phase, right? Where you end up having to discretize your governing equations, either through finite differences, finite elements, or finite volume. I must point out here that finite differences are usually not used in CFD because they are only restricted to relatively simple geometries. So now I've shown here some mesh elements for a pipe, for instance. Now you have a hex mesh, which is a well-structured grid here. And so you have a well-structured grid, and then you have a tetrahedral mesh, which is unstructured. Now, if you look at these meshes, you'll see that we have some resolutions, or the mesh elements are relatively finer, closer to the walls of the pipes. This is basically to capture the boundary layers here. So those are some of the things you would have to ensure are properly done when you start working with CFD tools. Now, after you've obtained your solutions, for instance, one thing you have to do is then process your data such that it makes sense. So those are some of the things that you need to actually consider. Now, when I move on, here, it's almost impossible to talk about CFD without talking about the governing equations, which most of you already know. If you've taken fluid transport, you've taken heat transfer, you know some of these governing equations. So I wouldn't derive it, but if you're interested, we'll talk about it. Anyway, so CFD is mainly based on the conservation laws or conservation principles, which is the mass and mass momentum balances. You may have to actually solve an energy equation in addition to the mass and momentum balances in CFD. But then fundamentally, in all of this, almost all of your simulations, you would have to solve the mass and momentum equations. Now, if we take the momentum, mass and momentum equations, for instance, and we make some simplifying assumptions, for instance, by saying, well, the flow is incompressible, for instance, then we end up with the famous continuity equation, which is basically saying the divergence of your velocity is equal to zero, which is basically what you've done in terms of mass fluid transport, which is mass flow rate in should be equal to the mass flow rate out. Basically, that's what it is. Now, when you take a look at the Navier-Stokes equation in this case, by assuming incompressible flow, you've simplified the problem a bit, and it is a statement of Newton's law, basically. So for a given fluid element, this is just the acceleration term, and then you have the sum of forces, which is the pressure gradient, as well as the viscous stresses, and then any external forces, which is your body force terms here. Now, when we take a look at the Navier-Stokes equations, for instance, first of all, you cannot solve the momentum equation without solving the mass balance equation. So those two equations are coupled. Now, for very simple flows, you would be able to get maybe an analytical solution, but for real flows, you still need to basically solve this coupled nonlinear PDEs. So, well, it's easy to show here that the free parameter, in the absence of body forces, let's say you have a flow through a horizontal pipe, for instance, it's easy to see that by basically non-dimensionalizing with appropriate variables, you are able to see that the Navier-Stokes equation, for instance, depends on the Reynolds number. Now, this means that if you increase the Reynolds number to at high Reynolds number, your inertial terms, basically your viscous terms reduces to close to zero, or they are not going to be dominating the flow, but then the inertial term is going to be dominating your flow problem. So this is something that you are used to, which is that at low Reynolds number, you have laminar flow, the fluid behavior is orderly. And once you keep increasing the Reynolds number, you transition, you begin to see some chaotic behavior, but the flow is still laminar, just that in the transition state. And once you increase this Reynolds number to a certain extent, the flow becomes unstable and becomes relatively chaotic. It becomes chaotic. Now, let's take a look at just the streamlines now. Once you look at this flow in the turbulent regime, you see that you've basically enhanced mixing in the turbulent case compared to laminar flow. So this is really important for a lot of the engineering applications. And that is what you would seek for your case of a heat exchanger and all of the things we do and processes that we handle in chemical engineering. You would want to get as much as possible a turbulent flow. So this is something you need to take care of. Painting that was actually painted by Leonardo da Vinci back in the 1500s of turbulence. This is where you would see that it's quite chaotic, it's disorganized. There are a number of eddies out there. So one attribute of turbulent flows is that it is disorganized, it is chaotic. It looks random, but it is not random, because you can actually obtain this behavior, chaotic behavior, from ordinary differential equations as well, just nonlinear ordinary differential equations. Now, some people when you do go into CFD, one thing you have to be cautious of is people talk about randomness of turbulence. Now, turbulence is not random, it is chaotic. And one of the reasons is that it is not repeatable. Reason being that it is sensitive to initial conditions. So you might be able to start from a slight initial condition and you end up with very different results. So that is why turbulence is considered by many as random, but for a modern view, it is not. And another key feature of turbulence is that you are basically enhancing mixing and then the dissipation of kinetic energy. You end up having large range of length and time scales as well in turbulent flows. And then it is three-dimensional. So three-dimensional, time-dependent, and rotational. So if you have a potential flow, for instance, it cannot be turbulent. So with all of this, I'll just give you something to look at, which is that this is the case where you have convection of air, for instance. And in the convection of air problem here, where you are heating the bottom plate, and then the top plate is maintained at a constant temperature. Now, by so doing, the air at the bottom is actually less dense compared to the air at the top. And so you end up having motion of the whole domain. Now, when you look at this flow, it is turbulent behavior, because you can kind of identify eddies at a very large scale, which is basically at the level of your domain. And within those eddies, you can kind of see very, very small eddies as well. So you have a large cascade of length scales within even this simple flow. You could see this in even stir tanks as well. So stir tanks are basically turbulent, operate under turbulent regimes. So you see this similar behavior even in stir tanks as well. So, well, how then do you treat, or in CFD, how then do we treat turbulence? Well, there are at least three approaches to treating turbulent flows, which is that you can do a Reynolds averaging of the fluctuating components. You could do a large eddy simulation, or you can just say, well, I'm just going to go brute force and solve the Navier-Stokes equations, resolve all of the infinitely large length scales involved in turbulent flows. Now, that also means that you are going to need a very fine mesh to be able to capture all of the length scales. And your computational cost is around the cube of your Reynolds number, which is quite expensive to solve. So mostly for engineering applications, you would most likely be either dealing with RANs or LES. Now, what are this, for instance? I'll illustrate a bit more with the RANs approach. So with the Reynolds averaging, you basically decompose your fluctuating component, which could be velocity, into a mean and then a fluctuating term. So you have your mean flow and your fluctuating term. So when we take a look at just the Reynolds decomposition, for instance, you are basically saying, well, my velocity, the mean component, is now independent of time. And then you have a fluctuating term, which is dependent on time. So what then you can do is, well, the time average of the mean value is just a time average of this. So and then you then substitute into your continuity equation. This decompose maybe velocity. You substitute that back into your continuity and Navier-Stokes equations. You then end up with equations that are time independent for the RANS approach. You would see out there people put a time dependent term, but once you time average, you don't get a time dependent flow for RANs. So that is something you need to take note of when you do your CFD calculations and when you're presenting some of those equations out there. Now, it looks like, well, by just doing time averaging, there is a challenge here, which is that because of the time averaging, we end up with extra terms, which are the Reynolds stresses or the turbulence stresses. And you need to find equations for those. So most of turbulence and even active research in turbulent flows or simulations are concerned about finding solutions, closure models for these last terms that you've introduced here. So you end up with 6 new unknowns that due to Reynolds averaging. So with every averaging operation, you end up with more unknowns than you can actually equations. So you need to find a way to actually resolve some of these unknowns. So one way that people do look at, or one of the popular approaches, is basically to say, well, I'm just going to compare whatever turbulence stresses to a molecular stress, which is something that you would see in laminar flow. So this is basically saying that, which is the Boussinesq hypothesis. What you are saying here is that the turbulence stresses are linearly proportional to the mean strain rate. And you know what strain rates are. And so you end up with an eddy viscosity here, and then these are your mean strain rate. This is just a correction factor to actually account for the fact that your continuity equation is 0 and you have a kinetic energy term that is basically half of half mv squared, basically. So with the Reynolds averaging for most CFD simulations, the most popular models out there are the K epsilon models, as well as the K omega models. So you make of the K epsilon model is that it's, and I've looked at just for you to look at the difference. Although I have, what you are doing is you are special components also time dependent, compared to a case with runs. But then the equations are relatively similar, but they are based on different mathematical operations, which ends up giving you some of these results here. So LES does capture large-scale turbulence directly, but the computational cost is much higher compared to the case of runs. Now, there are people who try to combine both approaches, which is you want to combine runs with LES for different regions of your domain. So those are some of the approaches out there, or you could just try to solve the equations directly. Now, with this, I'll try to illustrate a case with CFD analysis for a Kenix mixer. And here, it is for a crystallization process. So in general, when this is a typical process flow for pharmaceutical manufacturing of drugs or drug products. So you start with your synthesis step, and then you do crystallization to separate and purify your process. And then you do filtration, drying, and end up with, finally, you end up with your product. Now, the crystallization step basically determines the performance of both your drug product as well as your downstream processes. So if your crystallization step is bad, you would have issues with even drying and all of the final steps as well. Crystallization, supersaturation. So you want to create supersaturation either by cooling or maybe by using anti-solvent or maybe even evaporation to end up with creating supersaturation. And then you nucleate and grow those crystals. Now, in all of this, if you have supersaturation gradients, the distribution of your crystals would be bad, which may not be good for the performance of your product. So here, the goal is to come up with a mixer that can actually enhance or minimize some of these supersaturation gradients. And so there are a number of mixers out there, but here we are looking at a Kenix mixer, for instance. And what a Kenix mixer does is it's basically works in the form of Baker's transformation, where you think of dough, when the dough kneading machines, how it works. You are stretching the fluid element, you are folding, you split and stretch. And then so after each cycle, you end up doubling your striations such that you can end up having diffusion taking place. Now, why is this important to actually do this? If we can basically rely on turbulent flows to get our mixing done rapidly. Now, and it turns out that in certain situations, you can't actually rely on, you can't get turbulent flows. And so you want to approximate that behavior as much as possible. And so people do try to basically get multi-twisted layers and all that. But for crystallization, one challenge of using this approach is that you could easily plug your crystallizer or your device. So we looked at a different approach, which is that, we could look at the standard Kenix. And the question here we pose is, can we actually get better mixing with less elements? And if you're looking at this, maybe I've probably given the question away, but I would like you to guess which of these mixes would perform much better. Well, it's easy to guess that the standard, or if you have more elements, you would get better mixing. But that is not the case. That's what we found out. Now, in all of this, we've solved the continuity equation. We've solved the momentum equation for incompressible flows. And because we are dealing with transport of species, we also had that equation. And basically, for the boundary conditions, we imposed no slip on all of the walls. We also assumed that the flow is fully developed. And here are some of the material properties that we did use in our case. Now, in all of CFD simulations, you want to make sure that your mesh is independent of the solution you are getting is independent of the mesh, because if you have a coarse mesh, what happens is that your solution is going to be probably bad. So you want to keep refining your mesh until you get to a point where your solution is independent of the mesh. So your solution that you would obtain is basically not going to change, even if you change the mesh elements. But one thing you would notice is that with the mesh refinement, if you have more mesh elements, what that means is that you have more equations to solve. So your simulation would most likely take a much longer time to actually arrive at a solution. So you want to get to a point where you don't have too much. You want an optimal mesh, basically. So we have here 3 different meshes as an example. We have 1 million, we have 2.4 million mesh elements, and we have about 6.9 million mesh elements here. Now, after you've done your CFD simulation, just like in any numerical method, for instance, what you want to do is you want to make sure that your solution is valid. So you may have to validate it with either correlations or data out there, experimental data or correlations out there. So we did validate these simulations with data out there, with models out there, and we see that the solution we are getting from our simulations are actually well predicted by almost all the correlations. Now, we also perform experiments to make sure that we minimize, we get some of these results that we are actually seeing numerically. Now, the point here is that all models are wrong. And with correlations, you need to operate within, you need to operate within the ranges for which those correlations are determined. So once you get out of those ranges, your solution might not be valid. So we needed experiments as well. So this is a CAD drawing of the mixer actually that we did design and 3D printed it and used for the experimental validations as well. Now, the first thing to look out here is, well, when we compare different designs, the RL configuration as well as RR, what we see here is that the conventional standard Kenix actually leads to the highest pressure drop compared to the case with RR. Now, when you increase mesh, when you increase the gaps or the gap size, you end up decreasing the pressure drop, which you do know from fluid mechanics why. Now, in terms of mixing, we see here that the story is relatively different, which is that although you have the RL, the standard, which is a gap 0, performing well, you can actually get equal or even better performance with RR when you end up with less mixing elements, a gap of 0.5, which is quite interesting. So experimental results actually show that the same trends, but even better performance compared to what we are able to predict from CFD simulations, which is really interesting in this case. So one thing you also have to consider is the residence time distributions as well. So the new mixer actually improves or approximates plug flow performance better when you have gaps as well. So these examples actually highlight how you can utilize computational fluid dynamics to come up with either innovative mixers or new mixers, or even optimize existing mixers as well for applications such as crystallization or any chemical engineering process of interest to you. So with this, I'd like to thank you and also my colleagues at HKUST that I did collaborate with, and also people I work with at Deep Flow Systems. If you are interested in knowing what we do at Deep Flow, you can scan this QR code and basically give us a follow on LinkedIn. Thank you. I welcome questions.
Thank you for your enlightening presentation, Dr. Nyande. Now we'll move on to the Q&A portion of our webinar. If you have a question, feel free to raise your hand so I allow you speak. You can ask your questions.
Thank you, Dr. Nyade, once again. So I had this issue with this MPhil student. So you see the Nadia student you wrote, I think the one for the mass balance.
Yes.
I was of the opinion that it's too generic. So what happens if there are 3 pipes entering and maybe 1 pipe leaving? Generic. So what happens if there are 3 pipes entering and 1 pipe leaving? Like there are 3 pipes entering and 1 pipe leaving. Like, is there any variation? Is there any variation? I think my point there is. I think my point there is, can we simplify that equation to suit some geometry that we're working with? So we can write the general one, but can it be broken down to suit a geometry much better before we solve?
Okay. So yeah, if I get your question right, let me just show this again and let's. So your question is that for the mass balance equation, right? This. If let's say you have a case with multiple inlets and 1 outlet, right? Hello? Hello?
Hello, can you hear me?
Yes, I can hear you. So your question is that you have multiple outlets, multiple inlets, 1 outlet. Can the equations be simplified before solving? Is that your question?
Yes, that's my question.
All right. Okay. So, well, you could, but then it's not necessary for CFD simulations. The reason here is that once you've defined your geometry in your geometry creation, you are just going to impose these boundary conditions in there. So that is automatically taken account of. And if you look at this equation, you would see that. Okay, hold on. You would see that we have the divergence term, which accounts for any number of outlet or inlet situations out there. So that isn't necessary to simplify. So yeah.
Oh, thank you.
Yeah, the simplification might only be necessary if you are solving this manually by hand. Then maybe you have to do some simplification, but for CFD, that is not required.
Okay, so if I understand what you're saying there, because there's that grad function.
Yes.
That means that the flow can be coming from all these different directions. Is that what you're saying?
Yes. So basically, you are basically taking, if I can go out. I think I have something to maybe illustrate this. Hold on. So basically, if we look at the balance equation, which is the conservation, which we all do, what we can say here is that, well, you have multiple inlets, which could be multiple directions, maybe X, Y, and Z directions, for instance. So basically, you are accounting for the flow ins and the flow outs from all of these directions. So if there is no flow in a given direction, it's going to be 0. So if you don't have an inlet there, then that term is going to go to 0. So you end up with that general equation here, which basically is valid for all the situations, actually.
Okay, no, thank you.
No problem.
Thank you for your insight.
Since no one is asking a question, I have another question.
Okay.
On a much more philosophical level, okay. You know how CFD is computationally intensive?
Yeah.
So the question here being, it means that it might not be wise to evaluate all the possible options if you're thinking about optimization at the CFD level. Because sometimes depending on what we are looking at, there might be, I don't know, maybe 20, 50 different options. So the question is, what will be some of the pre-techniques that must precede CFD to kind of narrow the field to options that could be easily evaluated due to all this computational expense?
Okay. Honestly, you could, to answer your question, you could actually have parameterization, for instance, of your cases. So that is something we've done. We've run so many case studies. So you set it up in terms of when you are designing your geometries, right? You set it up in such a way that you can vary the parameters. So you have a range of parameters that can be varied for a given simulation. It might take a bit longer, but you could actually have that being done. But then other ways would be that, well, you could look at LAMP models where you don't look at something as complicated but interesting as CFD. So you could have maybe a simple, in terms of dimensionality, you could look at basically a simple one-dimensional case where you then simulate, optimize, and then you end up with a relatively, a set of solutions, Pareto solutions that could be useful in your case before even proceeding to CFD. Other approaches that you could actually think of it in terms of recent approaches of using data-driven modeling as well. So you could deal with some of those approaches as well.
Oh, thank you. Yeah. The second answer kind of really aligns with what I was also thinking. That yeah, solve some much more, reduce other models, shrink the space, and now come to CFD to evaluate your most promising options. Please, someone else should ask a question.
Yes, please.
Yeah, please. Who else has another question for Doctor?
Do you want me to represent it? Please.
Maybe I'll ask one last question. Sorry, guys. So I once saw this study in gasification. Well, in trying to optimize our parameters, what they did was, so they did some CFD simulations. Then they use something like an ANN to get a relationship between the input and output variables. Then they kind of optimize the ANN model rather. Please, is that process missing something?
So honestly, that is actually something that people are actually actively researching these days, and so it's not missing anything. Only thing here is that you don't have you want to have data, and then based on that come up with new optimal solutions. So it is active field of research, and so we don't know where that is going to go, honestly. But it's interesting to see where that leads us.
Okay, please. There's a question in the chat. Somebody is saying that he came late, so he didn't hear the softwares that can be used for CFD. So if you could, I don't know, hit on that again.
Okay, so with the softwares, you can use. There are a number of softwares out there. You just have to be aware of the numerical methods underlying them. So you could use ANSYS Fluent. You could use COMSOL Multiphysics. You could use OpenFOAM. There is STAR, CCM. There are a number of softwares out there. Only thing is that if you choose to go with ANSYS Fluent, for instance, you could get the student package, but you are limited. But you can still use it for some situations as well. Now, you could also go with OpenFOAM. But then there you would have to basically work in Linux. Now, OpenFOAM and ANSYS Fluent are based on finite volume methods. So if you do remember from Mrs. Momady's course, for instance, you started with a Reynolds transport theorem. So, and then converted to where you can then convert to a differential balance, as in the case of the Navier-Stokes equations. When you're dealing with finite volume methods, you want to start with the differential balance. You start with the differential balances and then convert to integral balances. So you're integrating over the control volumes. And so that leads to different sets of numerics. Console multiphysics, for instance, there's use finite element methods. So those are some of the differences that you need to be aware of.
Okay. There's another question which I'm going to read.
Yeah, I've seen it. So I'll try to answer that. So your question is, how can CFD incorporate reaction mechanisms? Well, you could use this reaction mechanisms in terms of, if we go back to, let's say, if we go back to even the Navier-Stokes equations, for instance, you'd see that you have a source term there. So that source term is your mass source, SM. So if you have a chemical reaction, then that will be your reaction rate. Your SM will be your reaction rate. So you have those reactions being incorporated into the balance equations.
Okay, Joshua, can I ask you a question? Joshua. Joshua, ask your question.
Joshua, your hand is up. You can go ahead.
It says he's unable to unmute. Please, that what's the name of the co-host? Please
type. You can type the
or
question.
you can type also. Joshua, try again to unmute and see.
Okay, thank you very much. So, hello.
Hello.
We can hear you.
We can hear you.
So my question is, for a young engineer learning the principles of design, where does CFD fall in the general syntax of design? Like, is it a first stage thing, or is it when you have considered like experimental design, mathematical modeling, physical modeling, before you go into, you decide to consider CFD?
Okay, so to answer your question, it is, I'm going to say it's not mutually exclusive. What that means is that in your design process, typically you could do basically experimental in your prototyping when you want to basically design an equipment. You could do fully experimental, which means that for every trial, you have to then go and refabricate a new equipment. And that is quite expensive. So what you can do here is that you can leverage CFD, come up with the optimal design, and then test. So that basically restricts how many times you have to iterate that design process. So you would still need to experimentally validate before you send your product out there. So that is basically what has to happen. Have I answered your question? Hello, Joshua.
No, that was Martin. Martin, has your question been answered?
He said yes.
All right, great.
Thank you, sir, for your insight. Who else has a question? Okay, so someone is asking, what are the future prospects of CFD as engineers? Dr. Nyande, would you like to take that?
Okay, so well, future prospects of CFD as engineers. So honestly, as an engineer, I recommend that everyone should know CFD, although the learning curve can be quite steep, but it is recommended to at least know what is happening in your processes. If you can actually leverage CFD, you would probably be able to design a lot of interesting equipment. So that is something that is recommended, but not everyone is going to be able to do it. So, well, if you can, just try practicing, go through, and it actually gives you a way to even visualize and understand some of the equations that you've probably seen being taught in the courses, but you probably haven't appreciated how useful those equations are. So CFD is actually very interesting, and it's something that you should try as much as possible to learn if you can. And I see another question, which is that how do we stay updated with latest advancements in CFD technology? Well, typically you would know about CFD by reading a lot of research papers. So typically you have CFD advancements in terms of numerical methods as well as applications, and then maybe software development. So the vast majority or the performance of CFD is basically related to the computers. If we have improvements in chip performance, for instance, then you can basically solve more interesting and more complex problems in CFD. And also you need relatively fast algorithms to be able to attack some of the challenges in CFD. So it is an actively evolving field, because up till now, nobody has even found solutions to, well, the Navier-Stokes equations. There is even a prize on it. If you can even give something meaningful with regards to Navier-Stokes equation, I think you probably would be able to get $1 million US. So it's still out there. So you can consider thinking about CFD as an actively growing field. Okay, so another question is, how does CFD stand with AI? Or what is the relationship there? If there is, if it's positive, positive, how do we leverage AI into CFD? Okay, so if you remember from the talk, you would see that there are a number of models out there to close, for instance, turbulence, right? So none of those models, apart from DNS, which resolves everything, but that could take you a lot of computational power to be able to actually achieve that. So what people do is utilize runs, Reynolds average Navier-Stokes equations, or large eddy simulations. So with both models, you need closure equations. So what people then do with machine learning, recent advancements are that you utilize machine learning models, neural networks, or any of those data-driven modeling to come up with closure relations for some of these models out there. And people also utilize some data-driven models to actually accelerate the computational time, basically speed up CFD simulation. So there is a lot of interest in applying recent machine learning techniques in CFD. So yeah. Okay, so there is another question. What are some considerations when choosing a mesh? So in the past, for instance, for your mesh, you would have to basically, well, let me show this. So Yeah. So in the past, if you had mesh unstructured grid, for instance, you would most likely have issues with the solution because its tech meshes are relatively bad. But there has been improvements in CFD technology or some of the algorithms that you are able to handle a lot of these meshes as well. Now, the reason people say mesh, for instance, is bad is that, first of all, you need more mesh elements to be able to fill the same domain compared to a hex mesh, which requires relatively lower number of mesh. So those are the first things to consider. So you have a lower number of mesh, your computational cost is relatively lower, or the time it takes for you to get results from your CFD run is relatively lower. Secondly, if you have a well-structured mesh, for instance, your mesh elements are aligned with the geometry or with the flow, unlike tech meshes, which are distributed all over the place. So what you can then do is, well, you need to look at the skewness of your mesh. You need to look at what are the aspect ratios and all that to be able to actually come up with a good mesh that works for your case. So there are some parameters out there or some criteria that you could use to actually come up with a good mesh. So if you have any challenges, you can consult some of the user guides or user manuals for most of these popular CFD packages, unless you are writing your own code.
Guys, if you have a question, on mute and ask. I see a lot of hands.
Dr. Nyandi, there's a question asking you to cite an example to help understanding how CFD technology is employed in the areas of wastewater and
one thing I would say here is that so long as you have a fluid flow problem, so long as you have any chemical engineering process or equipment could technically be simulated with CFD. So that is something you have to consider. For instance, yeah, that it's general, like the Navier-Stokes equation, the equations are valid for all of the systems that we handle. So technically, CFD can be used. Maybe the geometry might be more complex, which also means that you have to basically simplify your geometry, but not too simple that you lose the relevant physics. But you need to simplify it such that you can actually solve these problems. Yeah.
Hello, Dr. Nyandi.
Yes, please. And there is another one.
Okay.
Okay. No, please go ahead.
I remember those times when I'll be reading classification papers and the CFD ones. They'll talk about Eulerian framework, Eulerian Lagrangian framework. Like they're trying to model entry flow gasifiers, but they'll talk about some of them will say they use Eulerian for the fluid phase and Eulerian for the solid phase. Some of them will say they use Lagrangian for the solid phase and Eulerian for the. Please, could you I don't know, enlighten me a bit on that?
Okay, so actually with I think I could actually show you by example something I think here before I even go ahead in terms of explaining the equations. So what you are seeing. So okay, so with this example, which is your fluidized bed, right? If you look at the fluidized bed example here, you can see that, well, you can't see it, but then we have a solid phase and then a gas phase, right? So for the Eulerian approach, what you are doing for this multi-phase flow problem is that you end up basically having you treat both phases as continuum. But when you take an example like this cyclone, for instance, you are treating one of them as Lagrangian. It's more of you are basically solving the Newton equation in Newton's second law. So in this case, you end up basically tracking each individual particle, compared to the case of maybe an Eulerian phase where you basically have a volume fraction term, which then defines your phase. So it's the same for even the case with this third tank, for instance, where we have those particles. So each individual particle is being tracked. So that is the difference between an Eulerian phase or an Eulerian approach versus maybe Eulerian Lagrangian approach. And the equations are relatively different, but basically that is the approach. So in one case, you are tracking over the control volume, like your fixed domain. In the other case, you are following each individual particle. Have I been able to convince you?
No, definitely. You have explained it.
Okay, so let me look at the other questions as well.
Yeah, doctor, they are asking if you can recommend some YouTube videos or articles or books on CFD that seems impressive for training beginners.
Okay, so I would answer that. I think I missed out on William's question, which is, please, how complex is the modeling of multi-phase flows? Okay, so that ties in a bit with what Dr. Jude Bonsu has asked. And so now, basically, if you have a multi-phase flow problem, what you can then imagine is that for the mass balance, you have to solve for each phase. If you are dealing with an Eulerian approach, you have to solve the mass balance for each phase. So you have two equations, but then you know that the sum of the volume fractions in each location or control volume is actually equal to 1, depending on how you are treating that. And then for the momentum balance, you basically have this momentum balance, but you have extra terms, which are basically dependent on extra force terms, like the drag force here, which is the difference, relative difference in velocity. So you have to account for some of those challenges as well. And maybe if you have reactions, you have to look at the coupling as well. So it does complicate the problem, but it's something that you may have to do. And for the question of recommending articles or books on CFD, it's relatively easy to see a lot of the CFD tutorials or CFD videos online. If you just want to have an idea of how CFD works and all that, typically you might start with a book like Finite Volume Methods by, I think, Vestig and Malala Sekera, which would give you some ideas. But you have to be careful when you read almost all of those books, especially on turbulence, for instance, because it is an actively evolving field and it's quite complex. And so if you want the theory, those are some of the books. I recommend a book by Stephen Pope, for turbulence, because most of CFD is about being able to handle turbulence as well. Let me see. So you could also look at a book by Lamley as well. But for the numerical aspects, I think the book, a very small book by Suhas Patanka, should be able to help you understand finite volume methods. by Suhas Patanka. So those are some of the books. But in terms of the practical aspects, in terms of being able to actually do something with those equations, you need to be able to look at the user guide as well as the theory guides of whichever software you are using. ANSYS Fluent, for instance, has a very well organized user guide. So you can look at some of those user guides to guide you in terms of some of those tutorials. So you in CFD, you have to do the practical aspects. You spend a lot of time just building that muscle memory, and then you have to actually understand the theory. Then, yeah.
I'm going to seminar on CFD, so you can do it. Power to CFD.
Okay, so hold on. Okay, so okay, so let me take this one and then I'll come back. So the question here is: are there any gaps? Are there any gaps in the most recent CFD simulation packages? Can Malachi, can you at least elaborate on this one in terms of the question? You mean in terms of accuracy? Well, let me just try to answer this in terms of accuracy, for instance. Well, the numerics or the numerical methods are basically fundamentally for any package, if you are dealing with finite volumes, it's typically the same, right? So any package at all you take would have issues, but they are mostly valid for engineering applications, if I would put it that way. Yeah. So for experimental data, you may have to either have someone who does some of those experiments to help you validate it, or you have to do it yourself. Like, yeah, I had to do. You have to go to the lab, you fabricate your, if it is an equipment, you fabricate your device, you end up running those tests to see if you have agreement. But most likely, you would get relatively good agreements so long as you have the right models in there. Like if you've been able to actually model the process properly, you should have something that is relatively useful. Yes, there's computational fluid. Yes, you are basically dealing with numerical methods, and so everything you've done in terms of numerical methods, in terms of finite differences, for instance. So you could you would have to call back on that, and even more to be able to actually write your own CFD codes. Okay, so Caleb Ashali, you are asking if you could use some of these tools in chemistry. It's most likely you would be able to use some of these tools, but then it depends on your interest, right? Because if you are only interested in the chemical reactions without looking at maybe how your how those are affected by the transport processes, then you don't need maybe a CFD simulation to be able to come up with your reaction schemes. But then if you are interested in maybe applications beyond coming up with maybe reaction mechanisms and all that, then most likely CFD could be useful for your case. Yeah.
Hello, Dr. Nyadi.
Yes. Yes, please.
So I want to ask a question. Okay. Please, maybe think about it and don't answer. But so when I teach reaction, and that book Fogler, you see that it tries to do something like uses that MATLAB type software to model.
Yeah.
I forgot the name of that software, and use it Aspen to model. It also uses COMSOL to model. According to my abilities, I'm able to do both the MATLAB version and the Aspen version. But I don't have the skills to do the CFD modeling of, I don't know, either a PFR or a PBR or anything. So I wanted to just ask if you consider, maybe don't give an answer now, if you consider, I don't know, showing up and giving one lecture on how to use this, maybe we'll have to look for the right problem from Fogler. Then you become our Superman. You show us how to do, I don't know, maybe some packed bed reactor, all those kind of reactors that do exist, if that is possible. I don't want to put you on the spot, so you can just say you think about it.
Okay, I'll think about it. Okay, so I think we still have one more question. Isaac, can you, if you can hear, can you unmute yourself and then we can have a discussion on this?
Okay, thank you very much. Hello.
Hello. Yeah.
Yeah,
okay.
Because
yes,
I quite remember when I was once using a CFD software, and most of the times whenever I'm solving a problem, with the results I'll be getting, it will be diverging instead of converging, and I sometimes get stranded on that aspect. So I wanted to know if with the meshing quality, does it affect us with the results?
Yes. So the answer is so with most in terms of CFD simulation, most of your time would be spent on the geometry and the meshing stage. So you spend about 60% just getting the mesh, and you have to refine your mesh. Now, if we discretize, you look at the governing equations, you discretize it, you would see that you end up with a current number, which is basically the ratio between your mesh size and your time step. So it's possible that your divergence is coming from having too large of a step size. Your time step size might be too large, or your meshes are not well refined. So if you have poor quality meshes, you end up with divergence because you basically have those equations giving you a very bad condition number in your matrices. So yes, the mesh is one of the most important things. Beyond, apart from the physics, you have to actually deal with the mesh. Make sure that you've refined your mesh. So if you're getting divergence problems, yes, the first place to absolutely look at is your mesh. How are your mesh? And well, there are no actual definitions of a good mesh, but the first thing is that your mesh should be appealing to the eye. In terms of when you look at the transitions, it should be relatively smooth. So if you have a relatively coarse mesh, you are most likely going to, if you are not careful, you would get divergence in there. So that is something that you have to really take care of. Your mesh, really important. Okay. Okay, so well, someone is asking about phase change. So for phase change, again, that goes into your source term. So for each phase, you end up having a source term that accounts for that particular process that is occurring. So let's see. So yeah, basically this is your mass source term. So for each individual component, you have that here, which you can actually take care of. So any more questions? Well, please keep them coming. Okay, yeah, blessing.
Rita, you can unmute and talk.
I think admin has to, let me see. Can you kindly unmute her?
Yeah, Rita,
You've been
try again.
unmuted. You can speak.
Hello, Rita.
She says she's unable to unmute. Eish.
Okay. Isaac, yeah, go for it.
Okay, thank you. I want to know how relevant is CFD at our level, that is undergrad, because I realized that the equation governing the CFD model is too complicated, especially for me to understand.
Okay, so well, the equations are not too complicated for you to understand. But first of all, let me ask, what level are you in terms of, yeah, chemical engineering?
I'm in level 400.
Okay, so that, yeah, it means you've probably taken fluid transport and you've taken heat transfer. Now, so if you've taken all of that, what you already have is you already have the tools, okay? But you most likely would have ended up solving maybe simplified forms of these equations. Now, what CFD does is it gives you some hard skill set that you can actually use out there. So typically, yeah, you can utilize knowing CFD helps you in terms of do things that you wouldn't be able to do with by hand. So think of it from that point of view. Now, I have to say that I've seen in other places that even undergraduate students being able to do things with CFD simulations that were quite interesting. So we just think about it from that point of view.
So, Dr. Nyadi, if I'm to add a follow-up question, you know, undergrad, we used to solve questions like falling film and water falling through a pipe. Can we still do that on CFD? The kind of things that we used to derive.
Yes, and you would actually be able to do that in actually much more detail. So just think of the fact that for your falling film, for instance, you could actually end up simplifying this momentum equation, and then you end up with the same, maybe a one-dimensional equation for your domain. So here, if let's say it's not time dependent, you can look at it, convert this nabla term that into cylindrical coordinates, for instance, And once you do that conversion, you'd see directly that all of those tend to show up. Some of the terms we've seen or derived from that approach, where you basically assume basically some component and then scale, you would actually be able to do that. So that was something that I had to even do in my early days when I started CFD, was basically to come up, derive the Navier-Stokes equations in cylindrical and spherical coordinates. And I was given, I think, about an hour or so by my advisor at the time during my master's. So yeah, you could actually do all of those in details. So yeah. Hello. Okay. Yes, sure.
Hello.
Hello.
Yes. So you've mentioned crystallization as one of the areas where CFD is extensively applied.
Yes.
And I want to ask, so some of the challenges with modeling crystallization concerning the generation of a new phase and as such, how much of that does CFD come to answer? Or are those questions for another field or another area?
Okay. So to answer your question, what happens is that in in crystallization, you are looking at maybe a different set of equations, but you also have the transport equations out there. So you could use CFD to actually come up with maybe a good mixing strategy that would basically prevent supersaturation gradients, right? In your maybe your crystallizer. And then based on that, you can operate your crystallization process. But if you want to do a full modeling, you also need a population balance where you are basically tracking the number of crystals or number density of your solid phase that is being generated. So you could couple it. It's something that people are trying to do. But people are not yet there. We are not yet there completely, but there is still opportunity to actually do some research in that direction. Just that you have the population balance model, and then you couple it with the mass balance and basically momentum balances, and then you should be able to actually simulate your case.
Okay, so concerning the population balance, how much of that is a question for CFD?
So for the population balances, you could actually solve it with simplifying assumptions without having to resort to a CFD package. But one thing that you have to take note is that if you do assume that your crystallizer is well mixed, for instance, which is something very common that people do, right? You would most likely get a solution for a lab scale. Your solution may be valid for a lab scale crystallizer. But once you begin to scale up, that is where all of those mixing challenges pop up. That's when people then turn to people who do CFD to help them out, come up with a mixing strategy. So those are some of the things you have to consider. So typically, if to actually judge whether or not you need to consider mixing or not, you need to look at mixing time scales as well as your crystallization kinetics. Which one is your rate determining step? So if mixing is really, if your crystallization or your nucleation step is actually much faster than your mixing times, then you definitely have to consider mixing and try to improve your mixing. But if it is the other way around, where your mixing is relatively fast compared to your nucleation, which is most likely you would have to then you can get away with it. So those are some of the considerations out there. And so Rita wants to know, typically, sorry to take you, but okay, I see. If you have a gasification, you want to track particles. Okay, so now to answer your question, you want to know how to handle some of these cases. Well, now, if we look at these equations, you could actually have multiple phases in there. So you don't necessarily have to have two phases. You could have multiple phases. But then the question here is, what is of interest to you? So if let's say you can approximate or reduce the number of equations to solve, that would be great. If not, you may have to have separate different steps, sets of equations for each of the phases. And then you can actually solve them and then get some of those meaningful results. But in any case, a simplification might be necessary to be able to come up with a tracking. Or you could look at the modeling framework. So if you want just general averaged information, for instance, then maybe you may have to just resort to a continuum formulation for both of those phases, like an Eulerian approach, as Dr. Jude Bonsu asked. And then based on that, you may be able to actually simplify your computational cost. So those are some of the things that you may have to consider. But that work is actually something you would have to, you as an engineer, has to come up with and say, hey, these are the important processes that I need to consider. And then based on that, you develop your modeling strategy and your CFD simulations based on that. All right. But then if you have a follow-up question, please do ask out. Would like to hear more about what you are dealing with.
Okay, so I have a question here. So I have a student who's trying to do work which will end up in the design of a circulating fluidized bed gasifier. Am I right to say that the step between the literature review and attempting the final design will be to try, I don't know, different configurations using CFD so that we might see which one is better, I don't know, for hotspots, for mixing. Am I right in that way? So we can put, I don't know, maybe where the air is supplied at different places on the length, across the length of the CFB, that's circulating fluidized gasifier, so that you're able to see maybe what would be the best place to position it, what should be the best diameter. Because am I right that the CFD should be the thing we do before we try to actually weld anything?
Yes, you would. So to answer, I would say you need to actually come up with the optimal designs before you even try to fabricate. So the people actually are able to do experimental work, experimental studies without CFD simulations. Just that the question here is your performance or is your equipment performing, being well optimized? And you need to actually consider some of these steps before even moving on. But CFD simulations may not necessarily be the answer because in some situations, because sometimes it takes a much longer time to actually get results from CFD compared to actually doing some of those experiments, repeated experiments, and then they might be much faster. But in terms of design, if you are just starting out, it would be relatively cheaper to do some of these CFD simulations first come up with optimal design, and then you fabricate your gasifier based on that. And so you can also determine the operating parameters before you even begin some of those experiments. Because if we look at a circulating fluidized beds, for instance, the first thing you would have to look at is what is your fluidization, minimum fluidization velocities, for instance. Yes, to then you look at the circulations and all that. So those are things that you have to consider even before moving on to the next phase. Because with fluidized beds, for instance, when you look at the example in terms of the simulations I showed for the two cases, that was just a bubbling fluidized bed reactor, right? So with those two, you have one which is just a cylindrical geometry, and then one which is tapered. Now, actually, from CFD, we did find out that the tapered, the one with the conical design actually performs much better in terms of having much uniform mixing in the fluidized bed compared to the design which is just cylindrical. So yeah, those are some of the things that have to be considered.
Well, thank you.
I know, right?
Any other questions? Okay, seems like there's no other question. Doc, would you be available to answer any question participants might have later on via LinkedIn or something?
Okay, so well, if there are some of those questions, please do not hesitate to forward them or let them ask. I'll try my best to answer as much as possible.
Oh, great. Thank you very much, Doc.
No, Dr. Nyandino, thank you. This has been very fruitful. Like, I really had a lot of fun, learned a lot of things. This was beautiful. I think this is the best part. This is our third one, and it's actually the best. Yeah, I hope you come back again and update us on the new trends. Since you said the field is continuously evolving.
Yes. So honestly, I must say that everything we've talked about today is just trying to summarize some of the more detailed works out there. So if you notice, I haven't even touched on the numerical aspects. So for the numerical aspects where you begin to even try to implement, even if for a relatively simple one-dimensional geometry, I haven't touched. And for turbulence, for instance, there are books actually written, over 700 pages of books written for just turbulence. So there are a number of things still there that we haven't even touched here. So I just hope that this would be something that would at least ignite some interest for people who are interested. And maybe in the future, we could look at how to take this. Yeah.
No, okay, definitely. Looking forward to the future.
Yeah. So we want to say a special thank you to Dr. Abaginyande for sharing your valuable insights and expertise with us today. We truly appreciate you taking the time out of your busy schedule to be here with us. So we are looking forward to having more exciting sessions with you in the future. Also, I'd also like to express our gratitude to the Modeling Club for their dedication and hard work in organizing and coordinating this webinar. As we wrap up, I want to thank each and every one of you for your active participation and engagement throughout the webinar. Your questions, comments, and enthusiasm have made this a truly enriching experience for all of us. So until we meet again, enjoy the rest of your evening and take care. Thank you and goodbye.